I have the lights down, please?
Yes.
Okay, let's continue with the presentation of. Can I have the value?
Should be on.
I need to turn it on. Thank you very much. Okay, here we have what we have done up to now. The starting solution is B equal to 12A3 plus A4, which means that there are 12 units of X3 and 8 units of X4. And furthermore, that means that X3 and X4 are the basic variables, and A3 and A4 form the basis. A3 and A4 form, in this case, the basis. Now, in linear algebra, the word basis has a very precise meaning. Okay? So you have a set of vectors, for example. This is where you need to remember the fundamentals of linear algebra and understand the definitions very clearly, so that those definitions can come effortlessly out of your mouth. So the definition for a basis is this. Let's see, try to follow what I'm saying, and every word that I say, make it yours. So the way to make my words yours is you put in your mind, in your head, in your memory to be gone. Okay, so a basis for a set of vectors is a collection of linearly independent vectors such that every vector in the set can be written as a linear combination of the vectors in the collection. So a basis for a set of vectors is a collection of linearly independent vectors such that every vector in the set can be written down as a linear combination of the vectors in the collection. That's a good definition of basis. You can give it to a mathematician, and the mathematician will say it is correct. Don't give it to a lawyer, because the lawyer will say that he doesn't understand, or she doesn't understand what you're talking about. Because the word basis for a lawyer means something completely different than the word basis for a mathematician. And here we are talking about math, really. So who can say what my definition quickly, effortlessly? Anybody? I need volunteers. They say that Tennessee is the volunteer state. Go ahead. I need a volunteer from the state of Tennessee to go to the Alamo. The Alamo is the definition. You know, I've been in Texas many times, many times. I spent 27 years in Texas, and I've been in San Antonio hundreds of times, perhaps. And every time I went to the Alamo. When I decided to leave Texas and come to Tennessee, I thought, well, they came from Tennessee to Texas. It's now time to return the favor, and so I'm here to a lesser level, you know, of meaning. Here I am. The Texans sent me here to serve you. So who can tell me the definition? Go ahead, you.
Give it a shot.
Yeah, give it a shot.
A collection of linearly independent vectors such that each vector in the set can be written as a, trying to do without looking, but written as a combination of the vectors of within the collection.
In the collection.
In the collection.
Yes. That's nearly perfect, I think. Yeah. Okay, keep that in mind. So when you, so here what we are going to do is to write linear combinations in terms of the basic vectors. That's what we're going to do. Okay, what are the non-basic vectors? Here you have the vectors, all of them. 1, 2, 3, 4. Okay. At this time, the basic vectors are A3 and A4 at this time. And the non-basic vectors are the other two. So let's express the non-basic vectors in terms of the basic vectors. That is a trivial thing. You have done it before. A1 equal to 2A3 plus 2A4, and A2 equal to 3A3 plus A4. We've seen this before. And now we are going to, from this point on, we are always going to write this table. So in the algebraic method, the simplex, you just constantly do this. Okay, now let me show you the notation. On the left, you always have four things. The non-basic variables, and then you write the non-basic variables to the right, x1 and x2. So you introduce two columns for x1 and x2. And on top of each of the columns, you have the linear combination for the corresponding vector. If this is x1, the corresponding vector is a1. If this is x2, the corresponding vector is a2. And then you write the linear combination for a1 and a2 in terms of the basic vectors. So this is taken care of, taken care of. Now here we have on the left again, after the non-basic variables, then you have contribution, one entire row for something that I call contribution. The other one is called profit, loss, and the other one is the net increase. And we are going to add symbols. We are going to do this symbolically. We are going to work with letters instead of just words and words and words, because the symbols convey exactly what we want once we define the symbol. So the contribution, obviously, since we are thinking about a profit, then the objective function is a maximization problem, so the objective function coefficients are the profit. For that reason, the contribution, the symbol for that is C sub j, which is the same symbol for the coefficients of the variables in the objective function, C sub j. At this time, the profit that is lost by taking units out of the current solution will be represented by Z sub j. So we have C sub j, Z sub j. C and Z, both. And the net increase, as you know, is the contribution minus the profit loss. So the symbol for the net increase is C sub j minus Z sub j. And let's see here, what is the contribution for x1? Well, the objective function coefficient is 6. For x2 is 7. Now, what is the profit loss? Then it's the profit loss when you take 2 units of x3 and 2 units of x4 here, and when you take 3 units of x3 and 1 unit of x4 out. But the coefficients of those are 0, so you don't lose anything. It's 0 and 0. And then 6 minus 6 is 6, and 7 minus 0 is 7, and then you get the one with the highest net increase. Therefore, you say x2 is the entering variable. Okay, let's look at this picture to see which one is the leading variable. Okay, we have right now 12 units of x3 and 8 units of x4. So I'm going to color the units of x3 in blue. That's this 12, believe it or not, is blue. I can see it from here. I don't know about it there, but it's blue. And this is definitely green. You can see it from there. 8 units of x4 is in green here. So in this axis, you have the amount of resources available. 12 and 8. Now remember that the variable that we identified as the entering variable was x2. That's why in the horizontal axis here I have x2, always the entering variable. That's for x3 and this is for x4. And I got a2. So since x2 is the entering variable, then I write the corresponding vector, which is a2 equal to 3a3 plus 1a4. What's the problem with the sound over there, the noise?
You should keep,
This one here?
you keep the mics, brush it up against your...
No? Is it? About that better? See, I saw a little bit of manifestation of indifference here. You know, the noise was bothering me and you were very comfortable.
You said
So-
x2's the entering.
Excuse me?
X2's the entering variable.
X2 is the entering variable, and then we write the corresponding vector, you know, for x2, which is a2 equals 3a3 plus 1a4. This is a very important thing to write, and I wrote it next to what I have here, 12a3 plus 8a4. I wrote it right underneath in such a way that a3 in B is aligned with a3 in a2, and a4 in B is aligned with a4 in a2. If you can do that, that will simplify your life a little bit. Because look at what I'm going to do. This is called a feasibility test. And the result of the feasibility test I'm going to represent by means of a Greek letter. It's called theta. Greek letter theta. Okay. Then I reason like this. It's a kinological mind thing again. There is if you ask the following thing. How many units I have of x3? 12. Okay. Now, 1 unit of x2 replaces 3 units of x3. Then how many units of x2 do I need to replace all of x3? The answer is 12 divided by 3. Raise your hand if you agree with that. Okay, good. And then you repeat the same analysis for x4. You say, okay, I have 8 units of x4, and each unit of x2 replaces 1 unit of x4. Then how many do I need to get rid of x4? Is 8. So you want to be mechanical, you can be mechanical if you want to be. So you write B like I did, and the vector for the entry variable like I did, and quickly divide the top by the bottom. 12 divided by 3 is 4. 8 divided by 1 is 8, and choose the minimum. That's the feasibility test. Okay, let's see why the minimum. 4 and 8. Okay, here I am describing the process when x2 starts growing up, then x3 and x4 start going down. So you are increasing the level of x2, then they all start coming down. Okay? When you have here 4 units of this, you have gotten rid of the whole blue activity. The blue one is x3. So blue and green, you have blue and green. Okay, so blue starts coming down faster than the green, but both are coming down as you start increasing x2. Don't tickle me. Maybe it's this. Maybe I should put it in the one there. The belt. Well, I think this is going to be better. So the way to draw the blue line is very easy. You start with 12 here, and on the horizontal axis you place 4 here, and then you bring it down like this. The way to draw the green one is you have 8 starting here, and then you have 8 in the horizontal axis, and you connect them. And that's 4, and this is the rest of the green one. I color in solid green the quantities that actually remain. So in blue, nothing remains. In green, you still have 4 units. Okay? So, if you want to find graph these equations, because it's nice to graph the equation really good, then you need the equation, you need to draw these lines, then you need the equations. Well, the equation of the first one is 3x2 plus x3 equal 12. You can write that equation. And the other one is x2 plus x4 equal 8. I'm just giving you the equations of the lines in case that you want to draw them. Well, the important thing is these are the equations there. Well, I'm going to put here something important result. This is 4, remember here, look, I went from 12 to 0 here, but from 8 to 4 here. Then, this is very, very important, so this vector is not anymore 12, 8.3 and 8.4, it's 4 units of x2 and 4 units of x4, so it's 4a4 plus 4, 4a2 plus 4a4. It comes straight from this graph. Raise your hand if you understand that graph, that part. See, the way to reason is like this. How many units now do we have? We have to have units of the green one and units of x2. We have green and x2 is because that's what we are adding. We are adding a2, that's at the horizontal axis, and then blue goes away when we have 4 units of x2. You agree with that? So when you have 4 units of x2, you don't have blue, but you still have green. How many green do you have? Answer is 4 here. And then you rewrite this 4a2 plus 4a4. Okay. Now, again, raise your hand if that's clear to you. How about here? Is it clear to you? Mm-hmm. Raise the hand. Remember, I'm asking you to raise your hand so you can burn a few calories. You guys had lunch. You just had lunch over here and just moving the hand, even if it's little, even if it is little, you burn calories.
I'm a little confused that the theta step you mentioned, you chose the minimum.
This one here?
Yeah.
Okay, what is the rationale for the minimum? Very good question, okay? Suppose that I want to get rid of all of the green here. Well, what happens when I continue with the green after this point, okay? Then the blues stop, both are, you cannot stop them. So if you move to the right with x2, then green comes down and blue comes down. But notice that after this point, when you start increasing x2, the blue line becomes negative. And you cannot have negative activities. Yeah. That's the reason why you have the minimum here. Because you cannot reduce more than 12. If it becomes negative, then that doesn't make sense at all. You stop there, and this is a very mechanical test. It's called the feasibility test. Can I go into the next one?
So, 4 is your leading, 4 is the leading variable?
Okay, now the entering variable remains at 4, but the x here this x4 is 4 units. From the old one, instead of 8 units, we continue with 4 units for x4, the green one.
So x3 is the leading variable. So x3 is the leading variable.
No, I have one leading variable because x4 remains. See, look at this. Look at a4 here. A4 is here. A4 is here. So it hasn't left. It is reduced in quantity. It
So
hasn't
the
left.
x3 or
Well, look at this. Here, x3 was here.
Right.
Well, x3 is not here. So x3 is the leading variable. So x2 entering and x3 leaving variable. Good? Good. So the new solution is b equal a2 plus a4, and that indicates that x2 and x4 are basic variables. Now a2 and a4 form the basis.
So you just rewrote the equation in terms of A3 and substituted.
I could hear. Let me get closer to you. Okay.
So you basically rewrote the equation in terms of A2, A3, and substituted in for A2.
So you always write everything in terms
So that then you
for the you start with basic variables. Then you look at the non-basic variables and determine which of the non-basic variables comes in, and do the analysis to see which one of the currently basic variables leaves and becomes non-basic.
Okay.
Because when it leaves, becomes non-basic, it becomes equal to 0. So the new solution indicates that x2 and x4 are basic variables. Now a2 and a4 form a basics. Now look, I'm going to repeat this thing here that you have. a1, a2, a3, and a4. And now I color in red, before I have color in red, a3 and a4. I color in red now a2 and a4 because they are the new bases. So A2 and A4, as you must know, they are linearly independent. Try to get A2 from A4 or vice versa. See, this 0 here will not let you get these 3 ever. So you cannot get A2 from A4 or vice versa. So these are linearly independent vectors, and this procedure that we are following preserve that all the time. You will be able to get one basis to another until you get the optimal basis. Well, what I want, see, I understand this doesn't have to be perfectly clear right now in your mind. But I want this to be perfectly clear in your mind soon. I mean, you cannot just continue living with a hole regarding this thing, because you will not be able to sleep with tranquility. I promise you. You will not be able to enjoy life as much as you want to if you don't understand this very clearly, because that means that you are going to the OK Corral armed with a kitchen knife, and you've got to go to the OK Corral with your gun, because those guys are bad guys, and they are not going to say, "Welcome, son, sit down." They see you with a knife, they laugh at you, and they kill you. go to with your guns to the opaque corral, and you will go to the opaque corral tomorrow and day after tomorrow, and then that means you need to know this stuff. These are your guns. You follow what I'm saying? I like to be symbolic in when I talk. I like to talk. That's why I'm a professor. You know? So here, I color this in red. And the known is after this is everything is again and again and again the same. Okay, look, the non-basic vectors are expressed below in terms of the basic vectors. You know how to do this stuff already. So A1 is 2, 2, and that, I'm going to multiply this one by D1 and the one by D2. And that's the same as this system of equations. See, this system is the same as this. One more time. The second one is A3 equal 1, 0, and that should be the coefficients of the linear combination of D3 and D4. So that becomes that. This and this. And then you solve the system of equations and the coefficient. For the first one, D1 is 2/3, D2 is 4/3, D3 is 1/3, and D4 is minus 1/3. You just repeat the same thing again and again and again. So when you do a problem like this all the way from scratch, it takes a little bit of time. And I want you to feel really good. So I am not going to take away the opportunity to feel great one more time. You know, I promise you, as my name is Alberto Garcia, and actually I have a professional name that is Garcia-Diaz. I use it only for papers and all that kind of stuff, but when I am the man on the street, I'm just Alberto Garcia. But as my name is Alberto Garcia-Diaz, you know, I promise you that when I give you this homework exercise that will ask you to solve a little problem with the algebraic method, and you do it perfectly, I promise you, as my name is Alberto Garcia-Diaz, that you are going to feel great. Because you are going to see that and say, this is great, I feel great, I understand everything. See? I don't want to take that from you. So I'm going to give you a homework so you can practice, and you work with another person, and then when you solve the system of equations, you crank away. It's only systems of 2 equations that can be solved pretty quickly. In linear programming, we may have systems of thousands of equations. I will not solve that with the algebraic method, but I'm solving the little problem, the baby problem, the toy problem, I'm solving it with the algebraic method, because once we become mechanical, then you see that this kind of stuff does not need to be taken into consideration anymore. You can be very mechanical. But since we are engineers, it helps, it's necessary for us to understand the algebraic method, because once you understand, then you can be mechanical. What I don't think is all right is to be mechanical without understanding. A lot of people do that. As a matter of fact, my experience is that a lot of undergraduate students love that. When you just teach them, add this, multiply this, divide, combine, they say, great, I understand everything, they say. When you give them the algebraic method, they say, oh, we don't need this. I like the big picture. I like applications. It's just justification, it's rationalization. Then I go home and I cry a little bit for them. You know. Well, I have not cried for any of you yet. You have not put me in that position yet. Be nice to me. Don't make me cry, okay? Okay, raise your hand if this is clear to you, please. Okay, then this is mechanical again. Look, my table that I mentioned to you. Let's do it again. Okay, here I have the non-basic variables, x1 and x3. I put the values over there, the vectors, the linear combination for a1 and for a3. In all this, the only effort is this, really. This is the biggest effort, to get this and get this. That's all. Okay. Then you have this, and now you say contribution. X1 objective function coefficient is 6. X3 objective function coefficient is 0. Now what is the profit loss? The profit loss is, here you are going to take 2/3 of x2. 2/3 of x2, the coefficient of x2 is 7, is 2/3 of 7. And this is x4, coefficient 0, so it doesn't impact anything. And here it is 1/3 of x2, so it's 1/3 of 7, and this doesn't impact anything because it's 0, the coefficient of x4 is 0. So now you have this, and the profit giving up is this, and here you have 0, and the profit giving up is this, and then the net increase. And remember, I call this Cj, Z sub j, and Cj minus Zj. And the important thing is to look at the activity level that has the largest Cj minus Zj, the net gain. That's the net gain. Then this is 18/3 minus 14/3. You still have 4/3, and here 0 minus this is negative. So in that case, that is the entering variable. Okay. Here you have all the calculation. I'll give you 2 minutes to look at that. Yes.
Why do we start with our slack variables?
Why do we start?
Why do we start with our slack variables for the first basic solution, if you know that the contribution to the profit is 0?
Because the initial solution with the slack variables is trivial.
Because it's the easiest one to solve.
It gives you an initial solution right away, and it's feasible. That's the answer. But look at the stuff that I did over there and see if you follow that. It's pretty clear so far? Can I move on? Okay. So now, this is what we have, continuing with the analysis. We have 4 units of x2 and 4 units of x4. And not only that, we know that the entering variable is a1, then immediately place the corresponding vector underneath. Try to align the vectors a2 and a4, and that will be very easy. And now let's be mechanical. Divide 4 by 2/3 and divide 4 by 4/3. That's the delta test, that's the feasibility test, and you get 6 and 3, and the minimum is 3. And it corresponds to the green one. Okay, so this is the picture that you have. Now notice blue and green again. I have blue and green. Blue for x2 and green for 4/3. And when you have 3 units you get rid of all the green, so this one is 3. And when you have 6 units here, you get rid of all the blue like that. So those are the 2 lines. So if you want to get rid of all the blue, then the green one will become negative. That's when you stop, and you have 3 units there. And then the new solution will have 2 units of A2. Look, you still have 2 units of blue there. And the 3 units, the theta one is the new one. Theta value is the new one. Theta equals 3, so it's 3 units of A1. So that's the new basis. Raise your hand if you see it like that, pretty crystal clear to you. Okay, now look, this is the same thing that I have over there. Look, A1 is equal to 2, A2 is equal to 3, 1. I colored them in red because they are the new, look, we're going to have the new solution is A2 and A1. A2 and A1, they are basic vectors. I colored them in red. Again, they are linearly independent. Notice that you cannot get A1 from A2 or A2 from A1 by multiplying by a number. Okay. The new solution is B equal to 2A2 plus 3A1. That indicates again X2 and X1 are basic variables, and A2 and A1 the basic vectors and form a basis. The non-basic vectors are expressed below in terms of the basic vectors, and this is the exercise that we did. Yeah, at the beginning of the class I didn't want to erase that, because I thought we are going to see it again. So you do this, and you do this, and then you solve that, and you get this basis here. See, it's very mechanical, it's always the same. And the procedure is very logical. You cannot argue against this procedure. And so that is, let's move on. And see what we have there. We're going to see something really good now. Okay, look, that's A3 and A4, and then the rest of the table. And let's go one by one. Let's look at the non-basic variable. There are X3 and X4. Then the contribution of them are 0 for each one. Now, what is the profit loss? Then go over here. I says, okay, minus 1/4. A1, that's the coefficient of X1 is 6. Plus 1/2, the coefficient of X2, that's 7 for this one. For this one is 3/4, the coefficient of X1, minus 1/2, the coefficient of X2, which is 7, and then this is 2 and this is 1. And now when you do the calculation of the net increase, you get 0 minus 2 minus 2, and 0 minus 1 is minus 1. And now when you say, what is the entering variable? Say, there is no entering variable anymore. Why? Because we have the optimal solution. We have the optimal solution, and then you stop. That's the homework. I'm going to give you a homework like that. And when you put that stuff over there, you feel good.
Now, how do you know that's the optimal solution? Because there's no more contribution? Or the negative?
Excuse me, say that again?
Well, I didn't know how you know this is the optimal solution.
Okay, the optimal solution is because this is the net gain. The net gain, if the net increase, if it is negative, you shouldn't do it.
Okay. Both of them.
Both of them are negative. So we recognize an optimal solution when the net gains for all the variables is 0, of course, or negative. So
So now, what is the optimal solution? The optimal solution, we have this one, b equal to a2 plus 3a1, and that means x2 equal 2 and x1 equal 3. And the optimal basic solution is x1 equal 3, x2 equal 2, basic variables, and the non-basic variables, the slack variables in this case, x3 equal x4 equal 0, and z is equal to 6 times 3 plus 7 times 2, 18 plus 14 is 32. That's the optimal solution. Okay, let's review what we have done. Okay, let's see.
I'm going to try to put things like in a rather simple but organized way to see what we have done. Okay, we started with this. Look, 12 and 8, and we have a1 equal 2a3 plus 2a4, and a2 equal 3a3 plus 1 a4. That's what we had at the beginning. Then in here, I call it the 0th iteration. I don't count it as one yet because it's just the very beginning of the whole thing, what I have. And then I am going to have my information arranged using this kind of format for my table. What do I have here? I have x3 and x4, and I call them basic variables. Now I'm going to skip this, don't worry about it. And in here I have one column for x1 and x2 and x3 and x4. And at the first iteration I have -6 and -7 here, and 2, 3, 2, and 1. Now let me tell you what I am doing with the first row. This is pretty simple to understand. So if z, when I erase this, if z is equal to 6x1 minus 7x2, like that, I can write it down like this: z minus 6x1. Oh, the other one is plus, I'm sorry, plus. Okay. Minus, this is z minus 6x1 minus 7x2 equals 0. So I can always write the objective function as an equation. Why not? All I have to do is to do that. And that's what I'm doing here. That's why I put the negative. So instead of Cj, listen carefully, instead of Cj minus Zj, I'm writing Zj minus Cj. So in my table, I switch from C minus Z to Z minus C. Do you see? I'm playing with words there. Okay, in case that you don't know. When I asked this question to a person, and the person knew a little bit Spanish, I said, I switched from Z to C. And, you know, and from Z to Z, because before I have C minus Z, and now I have Z minus C. And I asked the guy, do you see? And the person knew a little Spanish, and he said, see. And I understood, of course. Yeah. So remember, here I'm going to get the negative of the gain, the negative of the gain. See, I call it Zj minus Cj. And here I have the value of the solutions. Look, 12 and 8 because x3 equals 12 and x4 equals 8.
And those that are not in this box are 0 because they are non-basic variables, as you know. Everything that's non-basic is equal to 0. So this is a good table to arrange all my results. The next thing is I have this. That was the next thing. Let me show you. I can do better than that. You see it there? Okay. And then I noticed that the basic variables were equal to 4 and 4. So that's why I have this table like that. And again, I continue in the next iteration. I'm just arranging my results in this format. I'm not proving or doing anything anymore. So then in the first iteration, I have x2 and x4 as basic variables, and they have the values were 4 and 4. And all the analysis came from these two. And then the zj minus zj, I have the negatives. Before I have 4 over 3 and minus 7 over 3. Now I have minus 4 over 3 and 7 over 3. And these coefficients, look, 2/3, 4/3, 1/3, and minus 1 over 3, I put in here. Same like this, look, 2 and 2, and 3 and 1, I put in like this. 2 and 2, and 3 and 1. So instead of putting them as a row, they are here like rows, 2 and 2, 3 and 1, I put in them like columns because it works according to this table. Look, 2 for x3, 2 for x4. This is 3 for x3 and 1 for x4. Same like this. And the same thing here. So 2/3 and 4/3, then you put a column. 2/3 and 4/3. 2/3 for x2 and 4/3 for x4. Okay? 2/3 for x2 and 4/3 for x4. The other one is 1/3 minus 1/3. So I put it like that. That's the way to arrange my results. The next one is that one. Here again, you can see it. You can see there the two, the previous one and this one. And the basic variables are x2 and x1. And the values of the basic variables are x2 and x3. And then I'm going to write 1/2 and minus 1/4 as a column, and minus 1/2 and 3/4 as a column to summarize the result of this iteration with x2 and x1 in that order, x2 first, x1 first, second. And here I have 2 and 3, and these are the coefficients or the linear combinations. So every time I in this part of the matrix here, and for these two columns, and for these two columns, notice that in this column I'm putting the coefficients of the linear combinations here. Like we have 2 and 2 and 3 and 1, 2 and 2 and 3 and 1. This is 2/3 and 4/3 here, and for this one here, and for this one 1/2 and minus 1/4, then this, and for this. Okay. And here, remember that I had minus 2 and minus 1, so I put that one, 2 and 1. I have arranged the results in that way. Okay. Now, this column is for x1, this is for x2, this is for x3, this is for x4. So in here, for x1 and x2, okay, I use these two columns, 2 and 2, and 3 and 1. Here is for x2 and x4, okay, x2 and x4 and x2 and x4. Then I need to use this is for x1 and x3, but this is for x1 and x3. x1, look, and x3. So I have the column for x1 and the column for x3. And this is for x3 and x4. Then I use these columns. So the reason I put this separate like this, not like together like here, or like here, is because this is for x1 and this is for x3. And because of the example, small example, I happen to have here x1 and x2 together, I happen to have here x3 and x4 together, but if I gave you 10 variables and so on, that's not going to happen. They are going to be separated, like I'm doing here. So this example is very representative of the real life situation. Okay? So all I have done here is organize my work, and I will proceed like this. I take that out. I don't need it anymore. No, I don't need this anymore. So I have summarized here everything I have done. Check it and you will see that everything is there. In my notation, I stop when the numbers on the zj minus cj row are positive. Because I switched the subtraction to z minus c instead of c minus z. Okay, let me give you more ways to interpret what we have done. If you want to know in this table what is the entering variable, okay? In here you have x3 and x4. Now, what is the entering variable? Okay, then the entering variables in this case x2. So how do you know what is the entering variable? The answer, let's be a little bit mechanical. The one that has the most negative value in the z minus cj row. That's the one that has the most negative value is the entering variable. So, entering variable here selected was x2. So in the next table I should be able to see x2, but occupying what spot? I need to determine what is the one who is leaving. Okay. Okay. Now